Have you ever noticed repeating patterns in nature? Maybe wondered if there's some kind of hidden mathematical language underlying everything, from the smallest atom right up to the vastness of the cosmos.
It's definitely more than just a passing thought. I mean, it really hints at these universal constants that seem to dictate the structure of our world. Like
Yeah,
I said, from a seashell spiral to maybe even space-time itself.
exactly. And today, that's what we're doing, a deep dive into two of the most, well, profound and mysterious numbers in mathematics. The golden ratio, usually shown as the Greek letter phi,
Right.
and Euler's number, E. And you've given us just an incredible stack of sources for this. We've got scientific papers on quantum mechanics, AI.
And historical documents, too. Ancient architecture, how plants grow.
Mhm.
It's a really diverse mix.
It really is. So our mission for this deep dive is to pull out the most important nuggets of knowledge, the key insights from all this material.
Yeah, we want to uncover how these numbers aren't just, abstract ideas.
Yeah.
They're fundamental constants. They reveal these surprising connections, optimal designs.
And maybe even clues to intelligence itself.
Perhaps that's part of the mystery we're exploring.
Okay, so to really get this connection, maybe we should first get acquainted with each number individually. Let's start with E, Euler's number. What exactly is this number? It seems to pop up everywhere in growth and change.
Right. Well, E is the base of what we call the natural logarithm. It's a super important constant, approximately 2.71828, and it keeps going.
Okay.
What's really fascinating about E is that it's not just irrational, meaning, the decimals go on forever without repeating,
Right.
but it's also transcendental, which basically means it can't be the solution to any simple polynomial equation with rational coefficients. It kind of stands apart mathematically.
Huh, transcendental. That does make it sound almost, well, mystical. Where did it come from? When did we first sort of become aware of it?
Well, its practical use first really came up in the work of the Scottish mathematician John Napier back in 1614, especially with his work on logarithms.
Late beer, okay.
And then Gottfried Leibniz used it in some letters in the late 1600s, but it was really the Swiss mathematician Leonhard Euler who cemented its place.
Ah, hence Euler's number.
Exactly. Around 1727 or so, he started using the letter E for it. And by 1736, it was pretty much standard. So while the ideas were brewing, its formal recognition and name are, compared to some other constants, relatively recent.
Yeah, it sounds like ease is kind of the new kid on the block compared to the golden ratio. Tell us about that one, because I know its story goes way, way back.
Oh, it certainly does. The golden ratio has this incredibly rich history. We're talking ancient times, Egypt, Greece. It's been around in human consciousness for millennia.
So like actual structures.
Yeah, the famous early examples of the Parthenon in Athens. Construction started way back in 447 BC, and its design seems to incorporate what we now call the golden section proportions.
Wow, 447 BC. So they had an intuitive sense of it, even before the math was fully written down.
It really seems that way. An intuitive grasp of aesthetically pleasing proportions. The first actual recorded definition, though, comes from Euclid.
Euclid, the father of geometry.
That's him. Around 300 BC, give or take, he described it pretty elegantly. Imagine a line, right? You divide it into two parts.
Wow.
The ratio of the whole line to the longer part is exactly the same as the ratio of the longer part to the shorter part. It hits this unique point of balance.
Huh. That's a neat way to put it. And the name, golden section, was that Euclid too?
No, actually, that term came much, much later. It was a German mathematician, Martin Ohm, in the 19th century who first called it the golden section.
Interesting how the names evolve. Now, speaking of history and connections, you really can't talk without mentioning the Fibonacci sequence, can you? Everyone sort of knows it. 1, 1, 2, 3, 5.
Absolutely essential.
Yep.
And that brings us to Leonardo Pisano Bigoa, who we know better as Fibonacci.
Right, Fibonacci.
He introduced this famous series where, each number is the sum of the two before it in his book Liber Abaci, way back in 1202.
1202. And didn't he use that famous rabbit problem to illustrate it?
That's the classic example. He described how a population of rabbits would grow under these very specific idealized conditions. Pairs mature, produce a new pair every month, never die.
A bit unrealistic for rabbits, maybe.
Just a bit. But the number of pairs each month perfectly follows the sequence. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and so on.
And the connection to the golden ratio.
That's the really amazing part. Centuries later, Johannes Kepler, the astronomer, was the first to actually prove it. He showed that if you take the ratio of consecutive Fibonacci numbers, like 8 divided by 5, or 13 by 8, or 34 by 21, as you go further and further up the sequence, That ratio gets closer and closer to the golden ratio. It's the limit.
Wow. So fast is hiding inside the Fibonacci sequence. That's
Yeah.
quite a connection.
It is a fundamental link.
And there's another name that comes up here, Edouard Lucas.
Right, Edouard Lucas. He was a French mathematician in the late 1800s. He's actually the one who gave the sequence its current name, Fibonacci sequence.
Ah, okay. So he named it after Fibonacci.
He did. And he also studied a similar sequence, now called the Lucas sequence. It starts with 2 and 1, but it follows the same rule. Add the last 2 to get the next. So 2, 1, 3, 4, 7, 11, and so on.
Okay. A variation on the theme.
Yeah, exactly. And guess what happens when you take the ratio of consecutive Lucas numbers?
Let me guess. It also approaches.
You got it. The limit is precisely the same, 1.6180339. Again, it really hammers home how fundamental this ratio is to these kinds of additive growth patterns.
It really does. And seeing it pop up like that, especially in nature,
Yeah.
it makes you think, is the universe just built for efficiency?
Well, it's probably less about conscious design, nature sitting down with a calculator.
Right, yeah.
And more about the sheer efficiency of how things grow naturally. Plants, for instance, they don't try to follow math patterns. They just grow in the most efficient way possible. New leaves, new petals, find the best open spots.
And that efficiency naturally leads to these patterns we recognize, like the number of petals on flowers.
Precisely. It's striking how often Fibonacci numbers show up. You find flowers with 2 petals, like Enchanter's Nightshade, or 3, like Trillium. Wild roses often have 5, bloodroot 8, cosmos also often 8.
Huh. So you can literally count them out.
You can. And sometimes you see Lucas numbers or related patterns, like Hepatica often has 6 petals. Daylilies might have 2 sets of 3. Daisies are a great example. They can have 21, 34, 55, even 89 petals. All Fibonacci numbers.
It really is like nature's blueprint just laid out there. And this efficiency, this optimization, it's not just petals, right? It's how leaves are arranged too. Phyllotaxy.
Exactly, phyllotaxy. The arrangement of leaves on a stem, they often grow in spirals, and the ratio of the number of turns around the stem compared to the number of leaves in that spiral often involves Fibonacci numbers.
Like what? Give me an example.
Okay, so like an elm tree might do 1 turn for every 2 leaves. A cherry tree maybe 2 turns for 5 leaves. A pear tree 3 turns for 8 leaves. Beech trees show 13. Pussy willows 25.
And this arrangement helps the plant.
Absolutely. It's optimal. It maximizes how much sunlight each leaf gets and how well the plant can collect rainwater. It's all about survival and efficient growth.
Survival through math. And what about those amazing spirals you see in, say, a sunflower head or a pine cone?
Same principle, just applied differently. In things like sunflower heads, pine cones, even the scales on a pineapple, new elements, seeds or scales, form at a constant angle relative to the last one, and they move outwards.
Okay.
This naturally packs them in most efficiently. And the angle that works best, it's related to, it's called the golden angle, around 137.5 degrees. It's basically 360 degrees divided by squared, or related to 360.
The golden angle.
Yeah. Using that angle leads to the most uniform distribution, the tightest packing. And that's why we see those clear spirals, often with Fibonacci numbers. Like a pine cone might have 8 spirals twisting one way and 13 twisting the other. Sunflowers can be even more dramatic. You might see 34 spirals going left, 21 going right, or even 89 and 55 on really large heads. It's not just pretty, it's peak packing efficiency. Plants were optimizing long before we were.
Incredible. It just built in. And it's not just plants either. I think I read something about bees.
Ah, yes, the bee family tree. That's a classic example, always surprises people.
Huh?
If you look at a male drone bee,
Okay.
he comes from an unfertilized egg, so he only has one parent, a mother, no father.
Right.
But his mother had 2 parents, a mother and a father. So tracing back the generations for that male drone, you get 1 parent, mother, 2 grandparents, 3 great-grandparents, 5 great-great-grandparents.
Whoa, the Fibonacci sequence again.
Exactly. It just naturally emerges from the reproductive pattern.
Okay, so it's clearly embedded deep in the natural world. It's like a fundamental design principle for growth and form. But its influence seems to go even further, beyond Earth even, which is just mind-blowing.
It really is. We see these widely considered a key constant in aesthetics, in art. People have studied its presence in human facial proportions, trying to link it to our perception of attractiveness.
So there might be a mathematical reason why we find certain faces beautiful.
The idea is strongly suggested, yeah.
Yeah.
And it's not just visual stuff. You find connections in music, too. Think about a piano keyboard.
Okay, piano.
You have groups of 2 black keys, then 3 black keys. That's 5 black keys total in an octave pattern. There are 8 white keys in that same pattern. And the total number of notes in the octave, counting both black and white, is 13.
2, 3, 5, 8, 13. All Fibonacci numbers.
Right there on the keyboard.
Huh. And architecturally, we mentioned the Parthenon, but it didn't stop there.
No, definitely not.
Hmm.
Its influence, or at least the use of similar proportions, appears in architecture throughout history. It seems to represent this universal idea of pleasing, balanced design that resonates across cultures and times.
A timeless aesthetic.
Seems like it. But then, yeah, we look beyond Earth, and the connections get even more fascinating, maybe even a bit eerie.
Like with planetary moons, I saw that mentioned in the sources. That seemed really wild.
It is pretty intriguing. There are studies suggesting that the distances of moons from their parent planets, think Jupiter, Saturn, Uranus, tend to follow a pattern related to a modified Fibonacci series.
How does that work?
It seems like a moon's position might be influenced by the positions of the two moons closer in to the planet, almost like they're maintaining this delicate gravitational dance using these specific proportional spacings.
Wow. Like a cosmic resonance, an even bigger scale. The planets themselves around the sun.
Yeah, there's a similar trend observed there, too. The average distances of the planets from the sun seem to follow the Fibonacci series, although there's an offset involved, possibly related to the planet's density.
So it's not perfect, but the pattern is there.
The underlying pattern seems to be there. There's even something called Butasov's resonance theory of the solar system, which is explicitly based on the golden ratio. It suggests Phi's importance goes way beyond Earth, maybe even connects into things like special relativity. It hints at a kind of underlying order in the cosmos.
This really shifts your perspective, doesn't it? We've looked at ease and kind of separately, but the sources strongly suggest they're not separate at all. They're deeply connected. How does that work? How do these two giants link up mathematically?
Okay, yeah. This is where it gets really interesting and reveals this kind of unified mathematical language. You know, the elementary exponential distribution and probability theory. It describes things like waiting times or radioactive decay.
Right, common stuff.
The solution to that relies on a specific value, 2 times the natural logarithm of Sev, so 2L and
Up
naught.
2ln.
And that exact same value also plays a key role in other advanced math, like in something called Riccati hyperbolic functions, which model certain types of natural growth and decay. So right there, you have E, because of the natural log, and Ive, locked together in solutions describing the real world.
So they're not just running in parallel. They actually interact within the math that describes how things work. Are
What?
there specific, theorems that show this convergence?
Yes, exactly. Some relatively new theorems actually demonstrate this. One shows something pretty amazing with the Lucas sequence we talked about earlier.
The 2, 1, 3, 4 sequence.
That's the one. If you look at the exponential relationship between consecutive Lucas numbers, as the numbers get really large, that relationship converges directly to Euler's number, E.
Wow. It becomes E.
Essentially, yes. And the convergence is incredibly fast. You only need to go like 16 numbers into the sequence to get E's accurate to 12 decimal places.
Yeah.
It's a very tight, precise mathematical link.
That's incredible. So precise. And there was another theorem mentioned.
Yes. The second one involves another mathematical expression that also contains lnc, the natural log of phi. It shows that this whole expression equals E only when a certain variable in it is set precisely to C.
So phi is the key value that makes it work.
Exactly. And furthermore, there's a whole new class of functions called hyperbolic functions that are built using Fibonacci and Lucas numbers. These functions specifically highlight this deep relationship between phi and E, with ln, playing this central role again, just like it did in that probability distribution. It really underscores that they aren't independent constants, they're integrated.
It really sounds like while getting a lot more scientific street cred lately, it maybe used to be seen as a bit more fringe or esoteric. Is that fair to say? But that view is changing.
That's absolutely fair to say. The scientific attitude towards the golden ratio is definitely shifting, quite rapidly, actually. People are recognizing its fundamental importance. It might have been, sometimes pushed aside into less mainstream areas in the past, but its role in modern hard science is becoming undeniable. It's driving new breakthroughs.
Like in something as fundamental as quantum mechanics, how does it even fit in there?
Well, there are researchers, like El Nashi is one prominent name, who are showing that the golden ratio plays a really significant role in quantum physics research. His specific theory, based on it, is even considered potentially Nobel Prize worthy if it gets experimentally confirmed.
A Nobel Prize based on, wow.
Yeah, it speaks to how fundamental it might be right down at the quantum level.
And outside of physics,
Yep.
chemistry, biology.
Yep. In chemistry has been identified both on its own and in combinations within chemical reactions. In biology, its presence is confirmed in the structure of DNA.
DNA itself?
DNA itself, yeah. And other complex biological structures, too. It builds on those earlier observations about plant growth, but finds it at an even deeper level.
Hmm.
Even in studies of the human brain, research on brain waves has established a functional role for the golden ratio constant, seemingly everywhere, from our genes to our thoughts.
Okay, this is huge. If E and L psi are this fundamental in nature, in our own biology, our brains, even potentially quantum mechanics and the cosmos, what on earth does this mean for artificial intelligence?
Right. This is where the implications get really deep and potentially transformative.
Hmm.
We know the number Hinel is basically the foundation for Markov processes.
Markov processes, remind me quickly.
Sure, they're mathematical models for systems that change over time based only on their current state, not their whole past history. It's this sort of memoryless property. And that's absolutely key for a lot of probabilistic AI, how machines make predictions or decisions based on current data.
Okay, so Enel is foundational for current AI.
Foundational. Now, combine that with the exact mathematical relationship we just talked about between Enel
It's
and...
the L and L connection.
Exactly. It strongly suggests that all those golden ratio phenomena, the spirals, the growth patterns, the proportions we see everywhere, might actually be a special case of these underlying Markovian processes that ESA governs.
Whoa, so the patterns in nature aren't just analogous to AI, they might be mathematically linked through E and phi.
That's the implication. The fact that it shows up across systems, from the subatomic to the cosmic, has already inspired many AI methods, even if indirectly. Things like genetic algorithms, neural networks, certain search algorithms that mimic natural optimization.
Right, AI learning from nature.
But this connection suggests something deeper. It leads to this hypothesis that maybe many AI methods are essentially special analytical sectors of the golden ratio itself, that AI is already, perhaps unknowingly, tapping into these fundamental mathematical harmonies.
That's a really profound thought, but we always talk about AI's limits, right? Like, it can calculate and predict, but it lacks genuine creativity, emotion, the human stuff. Does it offer any clues there?
That's the critical question, isn't it? AI can simulate thinking, perception, learning, memory, problem solving really well now. But models for genuine emotions, original ideas, true creativity, that's still missing.
And creativity is so core to human intelligence, adaptation, art.
Exactly. And this is where phi gets really intriguing again. It's often called an aesthetic constant, a constant of harmony. Remember Pythagoras? He believed harmony was the fundamental basis of the entire universe.
Harmony.
So if phi represents harmony and aesthetics, and it's mathematically linked to the E that underlies current AI, it suggests a potential pathway, maybe integrating the principles of the golden mean, the mathematics of harmony, consciously into AI design could be a way to bridge that gap towards more human-like creativity and maybe even emotional understanding.
So let's just recap this incredible journey. We've gone from ancient Greek geometry to the cutting edge of quantum mechanics, from the tiny spirals in a pine cone to the immense distances between planets. And we've seen how these two numbers, E and phi, which seems so different at first glance, are actually deeply, intricately woven together.
Yeah, it's like they form this coherent mathematical tapestry that stretches across literally all scales of existence. They're not just numbers you find in textbooks.
No, they're fundamental principles governing optimization, beauty, growth. Basically, how the universe seems to structure itself.
It really does make you look at the world differently. You start seeing these patterns, this underlying order everywhere. It's like a hidden language waiting to be read.
So, okay, the big question then, what does this all mean for us for the future? If this golden ratio, this constant of aesthetics and harmony, is so deeply embedded in nature, in us, and maybe even mathematically linked to the foundations of AI, what happens if we start deliberately weaving the golden mean and the mathematics of harmony into how we build and teach artificial intelligence? Could unlocking that next level of AI, truly human-like creativity, maybe even emotional intelligence, actually hinge on understanding and integrating these profound, almost beautiful mathematical harmonies?